from where you left off just before launching. Plenty of time for questions when we break for tea at 2:45. Thank you.
So I see there are much less people. Now I'll continue with some nice problems which use this derivation. The problems with bulk force are really quite blunt, more interesting when it is driven by the contour force on the droplet. And this is especially important because in microfluidics, droplets are mostly driven by surface forces, and microfluidics is really the most interesting application of all these things, because this is where gravity is negligible and all the things driven by adhesion are more important. Now let us look at two droplets, one big and one small. They are both non-wetting or partially wetting droplets, and from this diagram you see that the thickest precursor is in equilibrium with the bulk droplet, which is macroscopic sizes. But when the size of the droplet decreases, then the precursor becomes thicker. So if there is a precursor of a different thickness here, what happens? There would be a flux from a small droplet to a big droplet. It is as usually there are on all coarsening processes, they go according to the Matthew law. You know how it was in the Gospels, that those who have will have more, and of those who don't have will be taken what they don't have. So this will be a coarsening mechanism. Of course, there is also another coarsening mechanism through evaporation, but this is an additional mechanism which have different dynamics. There is more than this. Since there is this flux in the precursor layer, all this, of course, is very weak. Then both droplets will be driven in the direction of this flux, and the small droplet will go faster than the big droplet, and eventually it may catch up and they will collide. And so what is going on if we don't take into account motion and we just look at the flux of liquid is ripening, then it will go like this. We start with droplets, with several droplets, which are a bit of a different size, just a bit. And then what is going on? The poor is killed, then who is in middle class first becomes a bit richer, but then it is killed also, and the rest goes to the oligarchs, which are the richest. The largest drop always wins. Then we can do it quantitatively, because this would be the equation of motion in the precursor film. It will be a diffusion equation with some effective diffusivity. If it is thick enough to have hydrodynamic motion, then this will be this h cube or whatever divided by eta, and it will be driven by, it should be derivative here of the no derivative will come. Yeah, this is the joining pressure, and it may be just a molecular diffusivity. Then it will be constant. And here is the spherical cap which is in equilibrium with the precursor. The thickness of the precursor near this cap will be the standard thickness plus some change. This is how this change is computed, and it is with a coefficient that is about the ratio of a standard precursor length to the radius of the drop. So this is, of course, this effect which is significant for small droplets, for micro droplets. And then this is the Laplace equation. If we neglect small variations of thickness, this Laplace equation, and the Laplace equation we can solve very easily, and this will be the distribution of thickness, which depends on the radii of the droplets and the distances between droplets. So what is this? This is actually a solution of location on the location of any location actually, and this is the product over all distances, over all droplets with distances from this point. And so basically we have then we make use of these formulas for the here is the force acting on each droplet. The force acting on each droplet will be the integral over the contour, and since if there is more flux from one side than from another, then it will move according to the net flux. So what we obtain, so the more this force is actually proportional to the averaged over the interface of the gradient of h, and we can compute the velocity of the droplets. Here the motion of this equation for the velocity of this droplet, which will depend on distances between these droplets and all others. And this is what is going on if in this picture you have only migration without growth, just to isolate this effect, and you see there is such a this is initial positions, and they move. There are sharp turns when there are collisions and coalescence effect, and they gradually go into some direction. Eventually, they will all collapse here, far away. And this is the picture. So what we obtained before is just ordinary differential equations for the positions of these droplets. And so, and we can easily integrate these equations. This actually I did myself on Mathematica, and obtain these trajectories. Now there is another way. So, well, this migration of the droplets on the precursor layer is actually only theoretical, because nobody observed it clearly, because it needs a very smooth interface, and then it is spoiled actually by evaporation, because if there is evaporation, then instead of Laplace equation, we'll have Helmholtz equation, and interactions will decay, interactions with droplets. So Laplace gives strong interaction because there is only a logarithmic decay, and with Helmholtz it will all decay exponentially. Now there is already experimental process. Experimental process is motion due to changes in contact angle. And this here, for a comparison, I give, this is Fitzhugh-Nagumo equation, and there are droplets of one phase, say of higher concentration, which are created, and then they start to move. And sometimes, but in this case, sometimes they disappear, and sometimes they grow into a bigger pattern. Here, if there is a droplet of a real liquid, this cannot happen because there is a conservation law. And here are experiments. So first experiments on moving droplets were like this, that there was a chemical reaction in the droplet, and because of this chemical reaction, something was formed which was deposited on the substrate, and this substrate would become unwetting, and the droplet would to run away from there. It is like in Alice, the Mad Tea Party, where they dirtied their silverware and moved along the table. But it is problem like in carols. It is what would be when they go around the table, and so in this case the motion cannot be really continuous, because eventually this droplet will spoil all of the entire territory. The Japanese invented a better way. They had a droplet of this is oil, and this is water, and here is surfactant. And the surfactant is deposited here in the water phase. It is deposited on the substrate, and the substrate becomes more wetting for the oil. And inside the oil droplet, it is dissolved. And so this thing can move on, and behind the droplet remains really clear surface, and droplet moves, and because this process is continuous, it can move forever. By the way, why forever? What drives it? Actually, isn't it perpetual mobility? It is not, because eventually the droplet will be saturated with this surfactant, and it will stop. But it will run for a long time. And here is the picture how it runs. Well, for this, we can do a theory which is actually very similar to what is done in the pattern theory, in the Fitzhugh-Nagumo equation. So what you need here, you need equation for the surfactant adsorbed on the interface, and it is dissolved, and it is absorbed, but only outside the droplet. And so this equation, this equation we can actually solve if we rewrite it again in a comoving frame like this. We assume that the droplet is circular. The footstep of the droplet is circular, and then this and then this equation can be integrated in a nice way. So expressing concentration of the this is we just compute the integral kernel of this and compute concentration on the contour of this drop. You see, this is a long formula with Bessel function, and this is the integral. You cannot really compute this integral analytically, but it is very helpful because in order to know how the droplet moves, we need to know the contact angle, which would depend on this concentration, and so we have to know concentration only at the contour itself. We don't need the entire field. In this way, we can, since this is the change of concentration, and the velocity can be computed. This is this contour integral, this coefficient. All the parameters went into a single coefficient, and this is the concentration of the contour, which is obtained, which is defined by the integral on the preceding slide. And what we have here, we have a traveling bifurcation. That this parameter, if it is below this curve, then the droplet starts to move. Now, this is as a function of radius of the droplet, but the parameter itself depends on this radius itself. Because here is the dimensional radius, and this A is dimensionless radius. That's why there are different letters. And then, if we take it into account, then we can see that there is actually the mobility interval. This is already some algebraic derivation, and so above this peak, nothing moves. But here too, the large droplet does not move, but a small droplet does not move either. Why the small droplet doesn't move? Because the diffusion within the droplet is fast enough in order to make a concentration uniform. And this actually becomes easier in the non-diffusive limit. A non-diffusive limit would be in force for a large drop. So for a large drop will be some concentration on the front of the drop, and then it decays fast inside, and on the bottom of the drop there will be already, you see it exponentially decreasing concentration, and in this case actually everything can be done analytically, though through fancy. This is some Struve function. You always come to these special functions. Special functions were very fashionable actually in the beginning of the 20th century, but now it's where people investigated really all their properties and so on. But now there accessible again because Mathematica knows it, and you can plot this function with the same ease as you plot sine or cosine. And this is, and for this there are actually experimental data, and in the experiment they observed the velocity of the droplet as such a function of its size. And they really wondered why sometimes velocity increases with the size, and in other cases it decreases. Actually, at the beginning, some researchers got increase and others had decrease, and then came experiment where was both increase and decrease taken. And and here it is really very well explained, because for saturation of droplets there is a slow decrease, because the large droplet moves slower, and in non-saturated droplets there is a decrease, and the velocity comes to zero when diffusion is so fast that concentration is the same all over the droplet. And this is this is for some result actually for variable wettability. The driving force would be when there is no diffusion. The driving force will be just the integral, or just the integral of the change of a contact angle around the entire surface. And so, if the contact angle is smaller here, it will go into the droplet will go in the direction of where it is nicer for it to sit, where it is more wettable. Actually, we with Uwe did rather difficult computation for this with Airy functions and so on, which give more or less the same result as a more approximate theory. And here is a nice experiment in Potsdam, in Colloidal Interface Institute. What they have surface. It is experiment with on the silicon wafer, which is very smooth and which is covered still by an adsorbed layer of alkane. And on this sit other layers of alkane. And then when it starts to melt, in this experiment actually there are such ziggurat layers of alkane which condenses as a smectite. But when it is heated, a droplet of a liquid alkane is formed, and it moves. And here the wetting angle is different, dependent on the distance to the substrate. And so it is more wetting here, and so this droplet goes on and moves. And for this computation is actually very simple. And what we see there is that it is stable when there is when this angle there is a stable propagation when this angle is less than 180 degrees. This part is less than pi. And this is indeed the shape of this droplet. One can say that this such kind of qualitative experimental conservations is basically what we can achieve, because all this depends on a lot of parameters which are not known. You see, there is such an expression for the velocity. Well, these are contact angles, but contact angles they are more or less measurable, but always not always. But here, this parameter is the microscopic length, which would be usually unknown. Now, once we have such equations of motion for droplets and their interaction, we can really play quite a lot. Say, when there are several droplets, they will, when they move, since both of them affect the concentration of adsorbed surfactant, they will interact, and one can compute the change of the shape, because when they move, they change their shape. They move in this way. Then when they come closer together, they are repelled, and there is a kind of a scattering, and we can compute the scattering angle. Since we have all these integral expressions, so the problem is basically solved analytically, or almost solved. So it's solved till computations of some integrals. Then we can really play a lot and obtain, say, if there are these droplets, they will start to move, and if we have also some confinement, if they start to move, they repel each other, and because they exhaust the surfactant layer, so they repel each other. And if we have some confinement, what they will do, they will repel each other and go to become a grid. Or no, how we do it? I do it because this is a movie. It is supposed. Yeah, because here are trajectories, and here is the movie of the same thing. This is one of the same computations. So they start with random positions and eventually come to a grid. Oh no. Next, I can have still a bit of time to talk about instabilities, because all these processes with contact line, they are also subject to transverse instabilities, and which are always observed. Say, if you have something, a rim of liquid dropping on the glass, they will typically develop rivulets, and we don't care really what is going on the window, but there are important industrial processes. Say this is a coating process, and what we need is smooth coating, and this is what is observed as a result of instability. And this is some short-scale modeling. You see how this instability is developing. And then this is a process which is also very important, but not many know about this. This is immersion lithography. In order to in order to decrease the size of the features on the chips they are produced on the computer chips, then they use a water lens, and which just water acts as a lens, and it allows to increase the size maybe twice or something like this. So there is such a lens of this laser machine, which goes awfully fast, actually, with half a meter a second, not like in my microfluidics what we can treat. And here it can be spoiled in several ways. There can be bubbles on the advancing edge can form and go inside, and then droplets can be left on the receding edge, and this is this is actually an awful problem. And here it is so precise that when you model it, even the changes of temperature, minute changes of temperature, have to be taken into account. Really, well, I was consulting on this, but basically they just did it by more or less by hand, by trying all kinds of devices to change the motion of the liquid. How do we treat perturbed contact line? Here is this actually problem even is important even when the droplet is static, because instabilities can arise because of inhomogeneities, and also not every shape will be stable. So this is such a simple, intuitive approach of Dejean, that this if we perturb the interface, the perturbation energy will be proportional to the square root of wavelengths, but of the wave number, but then it will propagate, this perturbation will propagate inside the droplet at the distance of the order 1 over k. And this will give a relaxation response proportional to k. And this is, by the way, this is an unusual response, because if a contact line was a really two-dimensional feature, then all instabilities will develop as k squared, and here it is like k. And this can be made more precise, but not very much precise, because in reality the perturbation of the contact line leads also to pressure perturbation, and the bulk and pressure is already this is already non-local effect. The pressure will affect the entire droplet. But if we neglect this pressure perturbation, then we can obtain this Dejean's result quantitatively, because then there would be in the, of course, in the same lubrication approximation, and without external forces, the shape of the droplet is determined only by surface tension. It means that in the equations that we always have, the only thing will remain will be Laplace operator. And so if we neglect it and solve Laplace equation, we do obtain such a k response. Now, if we want to make this problem dynamic, what we can do, we can use we can use this equation. This is basically this Cox-Voynich equation, where velocity is equal the difference between the cube of the current contact angle and the cube of equilibrium contact angle, and this is the factor. The proportionality factor is what we computed. This includes the log of the. It is inversely proportional to the log of macroscopic distance divided by microscopic distance, whatever it is. So we don't really need really to know what is the mechanism, because any regularization of the contact line gives us this log, and there will be some coefficient which will depend on this particular mechanism. Then if we study just small perturbation, then it is enough to linearize this equation, and then it will be this is linear relation between the velocity and the change of the contact angle. And in this way, first of all, we can start from static perturbation and see that this is the straight contact line, meniscus, and if we solve the Laplace equation and obtain the change of the thickness here, which looks like this with such perturbations, and we see that these perturbations decay, and this already exactly they will. This is the equation for perturbation, just linear decay, and it is proportional to this k. In the same way, we can take a spherical cap and obtain for this. By the way, you see that here is if n equal 1 here, this is dependent on this is perturbation, the angular dependence of perturbation. If n equal 1, then it is 0, because at n equal 1, the droplet just displaces as it is, without change of shape, and so it will not return back. But if we take now a ridge, which we know it should be unstable, and for the ridge we of course we have instability at k, which is at k which is smaller than inverse radius. Then this becomes more interesting when we have a dynamic equation. So if we take the same system that we were talking about with surfactant, then we can observe here there are also instabilities. So here is again this equation for surfactant, and before we saw only one instability, which is motion, but it is also possible here to have such a symmetry breaking instability. And so we take how we study it. We take ask whether a straight line boundary will be straight line meniscus will be stable. Then for a straight line, we can for the steady straight line we obtain such a kind of solution. This, if we take a droplet, then we can we obtain such kind of solution for outside and inside the droplet. Then we introduce, as before, the linear dependence of the equilibrium constant angle on the concentration, and in this way, we set the perturbation problem. And perturbation problems of this kind, they are solved like this. We make a displacement of the boundary, and then solve the concentration equation for this displacement. And this is what we obtain. These are instability boundaries for a circular droplet, and you see here this is B is this parameter, which the larger is B, the stronger is dependence of the contact angle on the concentration, which drives it. And these are for all perturbation modes. This 2 is the dipole perturbation model, and you see that this is the prevailing mode. So when we increase B, first it will become a droplet will the perturbation such a dipole perturbation, and your instability will set on. And then we have here so we have here concentration and equation for the displacement of the contact line, which is what we have before, and which also includes the concentration flux of the inside the droplet, and obtain the instability of the contact line, which I showed before. Somehow this picture came before the formulas that justified. Yes, this was for the droplet, but this is for the straight line. This is for the straight line where the wave number is, of course, continuous. And here we have also we can have stationary instability, monotonic instability, and also oscillatory instability, depending on this parameter chi, where it is defined. Chi is essentially a parameter that contains diffusivity. Well,
does it go along the contact line, or is it like going back and forth?
It should go. It should go along the contact line. And well, this is only linear analysis. I didn't do it. And here this is for the circle, and as the this is as the radius of the circle changes, the instability moves to higher and higher numbers n, and so eventually it goes to the straight line limit. So I come to the end right in time. In this case, so this is conclusions regarding the droplet velocities. That they are computed with the help of these integral relations, and so it saves really a lot of computations, because everything is reduced to differential equations, and the motion in these interesting cases it's goes because of a gradient of capillary pressure, or which can be either because of interactions or because of changes of the substrate. And these are, by the way, there are a lot of unsolved problems there. Say there is such a thing as super spreading, which goes with a particular kind of surfactant, and nobody really knows how it goes. Then there are problems with meniscus with the surfactant, where there are nice instabilities. And these instabilities are not just toys, but actually, with this patterning, eventually people may succeed to have a small size patterning, and so that which will be much smaller than this than what is obtained now by modern methods. And so really small patterns, nanoscale, has to be created by self-organization. I think Uwe will talk about something like this. And then the contact line. This is what is important. That since it is 2.5 dimensions, that contact line is does not react as a usual line. It is and what is the last, the end, is that there are a lot of challenges here, because after all, the analytical methods that I was talking about, they are not applicable in many cases. You can do only as much as you can do, and what is needed really is some numerical routines that could span all the sizes. And so on nanoscale, we actually continuum also not may not be sufficient. And there were attempts really to combine molecular dynamics simulation with on small scales with continuum of larger scales, but they are not successful really so far. And then we lack also experimental verification of what is going on nanoscale at the contact line. Then all these theories that I was talking about, and basically all that exists, does not take into account surface roughness. And surface roughness is something which is always present in the most, and it is very difficult also to characterize. And this, after all, since this mathematical institute, the rigorous justification of these routines is also lacking. Actually, if mathematicians want to prove existence of or non-existence of these theorems of this solution, it is also an open problem. Thank you.
We have some time for questions before we break for tea. Any questions?
I have a general question concerning interaction of droplets. It's a reduced system, but you still have interaction in the complex surrounding media, so you still need to solve some PDE between droplets usually. How do you solve this problem?
Well, here you see in this approach for slowly moving and well separating droplets, we don't really need to solve anything. Well, we solve PDE there, but what we solve is the Laplace equation for droplets, and the Laplace equation has a general solution which is dependent on the position of the droplets. And so this general solution allows us to reduce the problem to the differential equations. And so whatever really I was talking about is such kind of a semi-analytical theory, because we are satisfied when we can reduce the system with the big PDE problem to the system ODEs, whatever large it is, because the system of ODEs any system of ODEs Mathematica solves in minutes. And so now, or to the computation of some integrals, which can be also done. Now this is what I call analytical solution. When we come to this, maybe at some time we can already consider PDE also as when we reduce the PDE to obtain it as a final solution. But actually, this I doubt, because the PDEs here are very difficult because of this scale separation. So I see you're looking and you want to ask something.
No, that's all. Thank you.
Any more questions? Thank you very much again, and we'll. Oh, sorry, I didn't see you.
So for the fault instabilities with the chemistry, did you ever have a case where you had an instability at k equals 0, a lateral one, that it would stick slip also
No.
in front?
No. In all these cases, it was on finite wavelengths, but it also can be, of course, yeah, it could be. Yeah, here I noticed that actually everybody is shy to ask questions. You shouldn't be.
Anyone else? Oh, okay. Thank you very much.